Okay. Today we're going to talk about selecting mechanical systems. In our study hall series, we started with, or basically, we're each week we're kind of progressing through the exam series. Last week was programming and analysis. This week is project planning and design. Why this is called selecting mechanical systems is because project planning and design is largely where you're evaluating what the pros and cons are of different systems in order to select them to be utilized for your project. Sorry, I'm going to pull this to the side so I can see all. Okay, and we're talking about VAV and VRF systems. So let's jump into it. Basically, the key questions that we're asking when we're designing a project, or at least in the early stages of design, and we're thinking about what mechanical systems we're going to be using, are as follows. So essentially, how large is the building? Each of the systems has implications about, basically the merits and limitations of what air and refrigerant can do. They have very real physical properties to them that needs to be considered based off of building scale. How the system is going to be used is critical. Is there going to be, or are there going to be many zones? Is it going to be a single zone? Do you need independent control in those different zones? Um, are we concerned with what the first cost is? Energy performance? Are we looking at the flexibility of the system? If we're doing tenant improvements, for instance, do we need high flexibility? Or is the owner mostly interested in maintenance and uh, comfort? Um, Another major consideration is ceiling heights. This is probably one of the most operable considerations, specifically because each project type usually has some sort of implication to the mechanical systems that we can use based off of what that project type usually goes for. For instance, like hotels try to limit the floor to ceiling height, or sorry, the floor to floor height, to save money on development. And so, air conditioning, for instance, usually has to switch to a more low profile system. Um, is our roof space limited, or do we have a fancy roof that can't really have any mechanical equipment? Or are there many small rooms or large open areas, and what sort of variability and use do we need to the mechanical system in that space? One moment, y'all. All right. Let's start with variable air volume. This is one of the more common systems that we use I guess, probably most commercial applications. So, tenant improvements for strip malls. We'll go through a few examples, but basically, this is ducted air delivery. Um, the system at the roof will basically, it creates the conditioned air and then just basically pushes it through the spaces that we're existing in, occupying. So that air handling unit will receive outside air, and then basically run its system, supply it through ducts into your various spaces. And so basically the thermostat is allowing a certain amount of conditioned air through. So that helps condition those spaces. It's limited by the fact that air velocity and temperature gets lost the longer you have to run. So that is a consideration. In order to have a balanced system, you have to return air back into the air handling unit, and then it basically filters it. You also will have some that exhausts out to the exterior as well. Let's talk about how VAV works. Essentially, VAV systems, they're a central air handling unit. So it basically will have, if you have a multi-story building, it'll essentially have a shaft that goes down. It'll push the air down to the various, and then it'll kind of just branch out across the other spaces at each level. The ductwork, of course, will be the method of distribution. So architectural detailing will have to consider ductwork runs. If you have rated walls that it's penetrating, sorry, pardon me. Um, if you have rated walls that it's penetrating, you're going to need some systems for that. And then likewise, if you're running, you could essentially need a horizontal rated system for that as well. Uh, you're going to have VAV boxes. That's where the valve is that lets a certain amount of airflow into the individual zones. And so in some cases, there could be reheating required where the zones require additional heat. So where are we going to use VAV? VAV is super common for office buildings, especially if you see like it's very popular these days to have like the industrial look. So you'll have kind of these big duct runs just through your space, and it'll just be spitting air out all over the place. Very common for schools. So if you have ACT ceilings in your classrooms, you'll see the supply and return in the ACT. Institutional buildings, very, very common. They're just not, large enough to essentially need, or I guess profile sectionally critical enough to need a VRF. We also use it for larger commercial buildings. So it'll kind of you'll have your package units spread throughout the building, especially for like high rises. You'll have your mechanical floors every so often. And then remember that this is going to have central mechanical rooms. So it doesn't mean that you only have one. You could certainly have many, but they're going to be a centralized distribution to spaces that are in its immediate area. Let's talk architectural impacts. VAV does require a significant amount of duct space. One of the things that the ARE does like to test is do you have the depth required for the profile of ductwork that you need? Something to keep in mind is that if you're using like a open web steel joist, like K joist or anything like that, you are allowed to pass ducts through that as long as it fits. So that's an option to have your duct run perpendicular to your structure. It just passes right through, so you can save some space on that. Um, it needs shafts, chases, and mechanical rooms. This is absolutely critical because it has to be distributed, unless you're doing an open to structure look and feel, in which case you don't really need any special casing for it. But you will need to, especially if you're doing more than I think 2 floors, you're gonna need rated shafts for your ductwork, your service ductwork. Yes, Diego.
Oh no, sorry.
Background noise. Okay. Um, Depending on which way your ducts are running, you'll always have to check whether it's parallel or perpendicular, and then basically just add, the amount of depth that you have of your structure, a little buffer space, and then your depth of your ductwork to consider what depth of ceiling plenum you're going to need. So it may require particularly large ceiling plenums. The central equipment may affect your roof planning or mechanical penthouse design. You do have to remember as you're designing the building that everything has to basically go back to the point of service. And that's absolutely critical for building planning. So it could have an impact on your spatial layout depending on where certain equipment is, particularly if you have an existing space. Um, Duct routing can conflict with structure. It definitely affects lighting, your sprinklers. They need to run underneath it if they're at all perpendicular, and your ceiling design. So, I mean, these things mostly it has to do with which way are they running and um, how many layers do you have and what space do they need. Some cautions related to VAV systems. They will require larger ceiling plenums, like I just said. There could be a lot of considerations. So like I said, with fire too, if you've got fire sprinkler systems going through, storm drains that are running lateral across your space, all that has to be considered. It certainly conflicts with beams, lights, sprinklers, your ceilings. All this has to be coordinated, so make sure you're doing a thorough review. You will have to coordinate your shafts, chases, and mechanical rooms, particularly look at them from a fire safety perspective. Um, there could be some critical implications for certain ductwork as it's running horizontally across your spaces as well. Reheat systems can reduce energy efficiency. Um, and basically your zoning is going to be absolutely critical for these systems. Pardon me a moment, y'all. All right. So the thing to note about zoning though is that effectively like VAV systems, while you have a thermostat for your different spaces, it's not as effective as a VRF system, which you'll see when we get into the VRF system notes. All right, variable refrigerant flow. Becoming ever more popular in more applications these days. Essentially, a variable refrigerant flow has an outdoor unit. It basically runs refrigerant to a controller. It will basically push more refrigerant out to these delivery locations, delivery units, whatever system you're going to use. But basically, it just runs super low profile in refrigerant piping. So you don't really have to consider ductwork. It's very, very low profile, very useful for when you don't have a lot of space, and particularly for existing buildings when you're reusing. So, like adaptive reuse, it's great for. But let's talk about some of these notes now. How does it work? So your outdoor condensing unit will connect to multiple delivery units inside. That refrigerant flow will essentially vary based off of the zones, like individually. That's what the BC controller does. Um, the indoor units, they'll serve individual rooms, zones. It can be as granular or as robust as you want it to be, but it's not super great for large spaces. Some systems will be able to do heating and cooling at the same time. It just depends on what kind of equipment you have. Pardon me, y'all, I'm struggling today. Um, so where to use VRF? This is actually critical. When it comes to the ARE, this is probably, particularly on the PPD exam, this is probably the most important thing that you can take away from this lesson is where to use it and why. It's great for renovations because it's super low profile. You don't necessarily know what kind of ceiling situation you're getting yourself into. The plenum might be, if there is a plenum, might be super small. You might not be able to fit um, ductwork at all, or it could be historically significant and you can't run ductwork through certain architectural components. Multifamily buildings are great. It's great for that. It saves a lot of space in terms of shaft delivery, especially as you get a little bit taller. Um, and it's excellent for hotels. I said one of the most important things about hotels, well, sorry, one of the most important things about certain project types like hotels, high density multi-family housing, basically like every inch of the building's height costs a lot of money. So they're really trying to reduce as much height as possible. So they don't want any ductwork running. Plus it saves on floor space too in terms of shaft area. Small commercial buildings, tenant improvements, independent zones. So if you have a program that just requires a lot of variability, so like labs, uh, healthcare, things like that, where you really need critical conditioning in independent zones in a relatively tight area. And then, of course, if there's really complicated runs to deliver air conditioning, you may want to just use VRF because its delivery is much simpler in terms of installation. The more that you turn ductwork, the less effective the system is. So that's just um, the I guess aerodynamics of how those systems work. You don't really want to have too many turns in your ductwork. Let's talk about the impacts on architecture. Um, this is going to require a vastly smaller distribution space than large ducted systems. The refrigerant piping, like I said, is super easy to route. It may not necessarily be historically accurate, but we do need to live with modern technology and historical buildings. So that's why we use VRF. Um, Indoor units, you still need to coordinate for maintenance access. There will be condensate drainage, so that's critical. You may have a drainage pipe going out. And of course, there's going to be some acoustical consideration. Not terribly different than VAV systems, except that you're going to have to protect acoustically, or at least consider acoustically the entire duct run, whereas here you really only need to consider the unit location. Outdoor units, they're going to have some considerations depending on how big it is. Usually they're pretty small, so it's not that big of a deal, whereas like VAV systems are massive. But you may need to consider like roof screening. If it's at grade, you may need to consider, is it going to be like in an occupiable space? Do you want it screened? Something like that. And then
Uh-uh.
if you're bringing in fresh air, that may actually be a separate consideration because this basically only recycles the air in the space. So you will need a separate air exchange system as well.
Hi, Kevin. Sorry.
Yes.
Is that a presentation that goes with your lecture?
What's that? Oh, I'm not sharing.
No, yeah.
Ah, man, get out of here. Let's go. Um,
Well, it's okay.
you had me just talking to you like this for this long. All right.
We're
Well,
talking about ceiling heights and usage of HVAC systems. I say, oh, there must be a graphic for this.
yeah, sorry. Okay. Well, hey, I'll give you kind of we'll run back through this. So, um, yeah, my bad. Sorry. All right, key questions. We went through these key questions. Whoops. How large is the building? How many zones? Are we concerned with cost, energy performance, flexibility, maintenance? Ceiling heights are absolutely critical. Definitely remember that for ARE. Is there roof space or is it a fancy roof? And then, what's the breakup of small and large spaces? So we're looking at VAV systems. This is the diagram about the VAV system. Pulls in outside air. Uh, it goes through the cooling coil, supplies it with a fan, sends it out to these are the VIV boxes. The thermostat controls those boxes, and it just lets a certain amount of heated or cooled air through. The notes on how it works, we already talked about these. Where to use VAV. Um, Definitely remember this. So if you're, preparing for PPD, take a snapshot of this. VAV is appropriate for office buildings, schools, institutional buildings, large commercial buildings, and it's going to have like centralized mechanical rooms. We talked about these architectural impacts, things to remember when designing for these. Duct space, shafts, chases, mechanical rooms, ceiling plenums are going to be quite deep, and then central equipment, and then of course duct routing is going to be critical to get through structure, lighting, sprinklers, so on and so forth. Cautions for VAV, you're going to have really deep ceiling plenums, conflicts with beams, lights, sprinkler ceilings, coordinated shafts with regard to fire as well. Reheating reduces energy efficiency if you have like long runs. And then zoning is not very flexible. And then here we go. This is the VRF system diagram. I'm gonna let you look at that for a second while I pause. All right, we're getting through this. I'm probably going to bed after this. Thank you for your patience, y'all. Um, how it works. The condensing units connect to those multiple indoor units. The refrigerant flows based on the zone demand. Um, it can serve individual rooms or zones, so it can be very granular. And then this can do, depending on which equipment you have, it could either do just heating, or heating and cooling. Where are we going to use VRF? This is critical for the ARE. I mean, in practice too. Actually, let's talk about practice and ARE. So, why I say this is I'm not spending a lot of time on practice for this one because, at your offices, you probably have a project type that, or two or three that your firm works on, and that's kind of your thing, right? So there's not, you know, there's not a lot of variability in needing to choose these systems in practice because usually if you have a project type or a specialty, um, uh, you're gonna know what it is. So if you frequently do renovations, you're probably looking at VRFs almost all the time. So that's kind of critical. I worked at a firm that just did schools K through 12 and higher ed. So it was pretty much we were pretty much doing package units VAV the whole time. Um, so we're going to use VRF in renovations unless there's already a ducted system there. You're pretty much just going to use VRF. It's just so much simpler to embed in an existing structure. Multifamily buildings, as we said earlier. Hotels, the critical piece was that floor to floor depth. They want to save money on the building height and make the flashy things more fun. Small commercial buildings, independent zones, and wherever there's impractical runs. I think this is about where we were. Um, so anyway, architectural impacts of VRF. It's going to require a lot smaller distribution space than VAV ducted systems. This refrigerant piping, it's much easier to route. Doesn't require any slope or anything. You just run it through. You can even pass it through structure, most structural profiles. Um, Indoor units, they're going to require access for maintenance, condensate drainage. So you may have a drainage pipe going out somewhere, and acoustical consideration. Outdoor units, we talked about, is it going to need to be screened, whether it's on the roof or down in a habitable site area? And then you will need a separate fresh air exchange system. So cautions. VRF systems do not, you have to remember this on the ARE. VRF systems do not automatically provide outside air. That is a separate system. So the air exchange is happening, but the VRF is just exchanging the air that's in the space and conditioning it through that unit. So you'll need a separate ventilation strategy to avoid sick building syndrome. Indoor units, of course, you'll require maintenance access, drainage for the condensate. You'll need to run power to it, and of course, acoustical design should it need it in acoustically sensitive areas. Um, if you have outdoor units, they may need to be screened and considered for maintenance access. And of course, your refrigerant piping limits can affect your layout, but it's not generally a big concern. It just may have a limit to how far it can go, and you may need to do multiple systems if it's a really, really large building. All right, let's talk comparison. I hope this did not format super well. Um, um, but this one, take a snapshot of this. It's really helpful. Basically, the difference between VAV and VRF is that your distribution is going to be through ductwork rather than for VAV and refrigerant piping. VAV is great for larger buildings with centralized service needs. VRF great for renovations, tight ceilings. The VAV ceiling is needs a basically a um, deeper plenum space from your structure above to your ceiling. VRF needs a shallower one. Um, We have ventilation. VAV just does the ventilation too because it pulls in outside air where VRF doesn't. VAV is centralized where VRF can be distributed. Um, Maintenance. Basically, the maintenance model for VAV is that they just go up to the unit, whereas for VRF you have to go to each of the units throughout the space. For zoning, VAV can zone, but VRF is much stronger at zoning. And VAV, we need to consider the ducts depths and shafts for that. So, and particularly with fire, when it comes to VRF, um, you'll probably you may or may not do any rated shaft on a VRF, but it's generally doesn't really need that because you just do a pipe penetration through a rated wall. I want to pull something up for this. Okay, so this is kind of critical for comparison. So you've got variable air volume, variable refrigerant flow, and I spelled that wrong. So sorry. But basically, the VRF integrates your conditioned air and then your outside air into one like ducted system, and it just serves the air to all the spaces from the source. Whereas VRF handles your heating and cooling in individual units, and it just runs refrigerant to it. So remember that difference. It's the key difference between the two. Bear in mind, don't assume that VRF systems will solve your fresh air requirements. You will still need to coordinate any air ventilation, and so you're going to need to possibly calculate like air changes per hour and stuff like that. That may pop up on the ARE as well. All right. Um, I'm going to pause real quick before we jump into exam, please, and collect my sinuses. So I guess, yeah, thanks, Diego. Give me 1 minute, and if you guys have questions before we go into that. All right. Monitoring the chat. I do not see any questions, so we'll go into some examples. Standard disclaimer on this, these are not as robust and complex as typical ARE questions. It's just a way to show you like the breadth of angles that the ARE may take to ask questions on this sort of subject matter. Um, so you may be asked about ventilation. Design team proposes VRF system for a small hotel. Um, they want independent temperature control in each room. We're reviewing major coordination items. Which issue should the architect raise first? And so whether the VRF system can provide outside air, whether the VRF system requires larger supply ducts than a VAV, whether VRF system eliminates the need for condensate drainage, whether the VRF system avoids all roof-mounted equipment. So the technically A and D could be possible. B is not because supply ducts. Um, and we know for a fact that VRF don't eliminate the need for condensate. So but A is definitely the more operable one. So that's kind of, an angle that it might take. Um, you may need to coordinate. Either you'll be given plans that you'll have to look through and see if there are any clashes. But this is kind of an example of a question too. During coordination, VAV system causes conflicts with structural beams, recessed lighting, sprinkler mains, ceiling heights. Which architectural issue is most directly associated with the selected system? Uh, Refrigerant charge limits, large ductwork and plenum depth, lack of zone level temperature control, or condensate drainage from indoor fan coil units. And we know that this one's going to be the large ductwork and plenum depth because it is a VAV system. Um, Owner priorities, long-term operations. You may be given figures for cost or energy and need to kind of analyze that. But here's an example: an owner deciding between VAV, VRF for a new office renovation. The owner likes VRF, reducing ductwork. Maintenance staff has never used them before. They prefer equipment that can be maintained centrally. What should the architect recommend? Um, Select VRF because reduced ductwork should always take priority. VAV because the owner operations and maintenance preferences are relevant selection criteria. VRF because it eliminates most mechanical maintenance requirements. Or VAV because it provides room by room control without terminal equipment. So this one might be a little bit more difficult to discern the correct one, but it is B. The VAV matches the maintenance preferences of the owner. Um, so adaptive reuse, ceiling height, you may be given sections that you have to study and see, if certain, conditions fit and work. An architect is designing an adaptive reuse office project in an existing three-story building. The existing floor-to-floor heights are limited, and the owner wants to preserve ceiling height in the main public areas. The program includes multiple small tenant suites with different occupancy schedules. Which issue should the architect prioritize during early mechanical coordination? Uh, Locating large supply and return duct routes, reducing the number of operable windows, increasing the structural bay spacing, locating all thermostats in a single central control room. We know we're not centralizing all the thermostats, that'd be weird, but that's going to be A. Your large supply and return duct routes really need to be finalized. Sorry, you need to, sorry, prioritized. Another example could be large office building considerations and considerations of a centralized system. A six-story office building has large open work areas, adequate floor-to-floor height, central mechanical space, and an owner with an in-house facilities team. Mechanical engineer studying a centralized air handling system with zone-level terminal boxes. Which coordination item should the architect review most closely during schematic design? The required ceiling plenum depth, shaft locations and mechanical room layout, guest room, fan coil access panels and condensate routing, refrigerant pipe length between outdoor units and indoor cassette units, or balcony locations for individual outdoor condensing units. And of course, that's going to be A. All the considerations for a, a VAV system. Oh, I thought I had another. Okay. Um, Pardon me a moment again. All right. Oh, let's stop sharing. Um, so that's kind of the critical pieces of VAV and VRF systems. I think the critical elements are going to be which buildings you use them in, and then what are the coordination considerations. Coordination generally is going to happen more in the PDD exam, but you may have some preliminary considerations like if the owner is looking at building height, floor to floor heights, and if the could be a question of like, can they fit 5 floors in here instead of four, something like that. Y'all got any questions, comments? You want to talk about something else?
Thanks, Kevin. When I get to PPD, I would really appreciate this conference.
Yeah, great. I'm glad you found it useful. This one was a tough one to really make like, I guess like super substantial. But like PPD is kind of weird when it comes to mechanical systems, and so I think it's important to look at it from like the selecting perspective.
Um, why is it that VRF systems tend to be higher maintenance? Just the sort of nature of the refrigerant?
VRF?
Uh,
V
yes.
yeah, so like it really depends on what kind of maintenance we're talking about. So like life cycle cost. Your maintenance cost for life cycle on VRF systems is going to be more expensive because they have to go to each unit and replace them, and you have to buy all these new units. And so, like each space that's zoned for a particular temperature control needs to be maintained and kind of tweaked, checked. So there's a lot more man hours that go into checking all the equipment, whereas with VAV systems, the ductwork is you don't have to maintain ductwork. You just have to go up to the system on the roof and tinker around with you know, the unit up top. I'm listening if you guys have more questions, but I have to blow my nose. All right, I'm back.
What if you're designing just an airflow system to complement the VRF system, how would that differ from how you design your ventilation system when it's a VAV system? Does that kind of make sense? Like, is it going to look really different how you duct things or?
I'm having a little bit of trouble hearing you on my onboard speakers. Let me get my headphones.
Okay, it's loud here, so it might be my fault.
No, my computer just like made the silly decision to have like a few speakers like above, you know, below the screen, but then there's other speakers that are below. Not very smart.
So
Okay. Repeat your question.
the question I'm trying to ask is related to like how do you what is the difference or how do you design differently a ventilation system that is just for air circulation to go with an already VRF um, space versus
Um,
designing a, a ventilation system that is VAV also.
yeah, actually, I've never done it. So I don't know exactly. I think it probably primarily depends on if you have plenum space. I gotta look into that. I don't want to tell you something that's incorrect.
Okay, yeah, I appreciate that.
Let me write this down. Get back to you on that.
I'm just wondering, like, if I could tell by looking at it, if it's what the system is.
Mm-hmm. Actually, let me just see if I can figure it out right now.
I suppose I can also always look things up.
I mean, I guess there's some ducting for that. Gotta love Reddit.
I
Yeah, I'll
mean,
show
I'm
this.
thinking like, when I'm thinking of like, ceiling fans and passive ventilation, but if you're gonna do ducting, I don't know.
Um, so yeah, this has VRF distribution, and it still has some ducting. I think the project type probably matters most with how this is done. Because like office spaces are just going to have a plenum, and so you won't really need the ducting. And it'll just flow, you know, kind of from over space to space. Um, but I gotta look into this a little more.
Okay, yeah.
You found a weakness of mine.
I don't know about that. But yeah, I appreciate that this was like it felt fairly simple and straightforward the way that you presented this.
Thanks. Have my other study halls been a little much?
I think the amount of content maybe has felt like it varied a little bit, but
Thank you for
yeah.
the feedback. Noted. Uh, making a note for this. Cool. Yeah, thank you. That's a really good feedback. I don't know. I think it's difficult with some of these concepts like structural load paths and stuff. I could talk with you for 4 hours on just that.
So, um, I don't have any other questions today, though.
Okay. Maybe we can stop a little bit early. I can get an extra 9 minutes of sleep before my 4 o'clock meeting.
I think that's smart.
Yeah.
Thanks
Diego, how
for
you doing,
showing
man?
up.
Yeah, yeah. I mean, it's critical. I thought about like, am I sick enough that I should cancel this? But I was like, nah, my core squad needs me.
Yes.
Thanks, Kevin.
Cool.
Really appreciate it.
All right, cool. Thanks, Diego. Thanks, Ari. Thank you for continuing to show up. Bring friends. I'm actually glad you didn't this time because I don't want this to be a first impression. But next week for sure.
Yeah, I'll keep telling people. Appreciate you. Feel
All
better.
right, have a good one, y'all. Thanks.